Any questions about the topic? Conceptually, it's very confusing. So, before we go into solving exact questions, I want to make sure that you know what is the conceptual problem that you can understand. Then I explain to you. It's very interesting.
Maybe we can start with the beginning first. Don't be scared.
So the question is, I think the issue is this: we know very common knowledge. We have very common knowledge about light. We know what light is. We think light is like a wave.
Sometimes say particle.
So we always think that light is a wave. So you agree with that? So then you try to recall what you mean by that statement. So when you talk about that, it means the light behaves like a wave. So you expect that when light when it moves like a wave. Actually, it's not moving like a wave, but its behavior is not displayed by a particle. Particle won't behave like a wave. So, for example, wave it moves in a straight line, and then wave will display so-called diffraction pattern. Right? So particle wouldn't display diffraction pattern. If you say you roll a bead, you just go straight. So when it hits on the wall, then it hits on the wall. So let's say if you put a lot of balls that is going through walls, all the beads will either go through or it doesn't go through. And go through or it doesn't go through. But then if it's a wave, then it's a different story. If it's a wave, then when it go past through this light, it doesn't go through, it will actually diffract. So light is very different from particles. So what light, when it goes through a small hole, it will diffract, and then it will interfere. So this is the basic notion about light as a wave. So assume that when we talk about this, then we always know what wave is like, behave like a wave. So we need to be very specific to describe the difference between a wave and a particles. Wave have properties. Wave is not a particle. Wave is a phenomena. Wave is not a particle. So if you have a bead say a bead made of glass and a wave, of course these two are totally different things. You don't expect a bead would behave like a wave. It doesn't make sense at all. Okay, so first of all, you have to make a very clear distinction that there is this incompatibility between a wave and particles. So specifically particles, it has this property which is not shared by wave. So for example, a particle is placed here, is all lumped. People call it localized. A particle is strongly localized. If a particle is located here, it will not be able to find it elsewhere. So this is common sense about particle. So it's what we call localized, and it's like a mass concentrated in one place. It cannot be simultaneously found at other places at the same time. Right? But wave is different. When I speak, you can hear me because mine was
frequency.
You have to be very specific about this. You cannot just say frequency. This is a phenomena. A phenomena is like this.
It's like how you say it spreads out.
Yeah. So why can you listen to me at the same time, and you also can listen to me at the same time? Because my voice, which is spread in the form of wave, it's spread out and fill up the whole room at the same time. So it is fair to say that my wave from the mouth goes into the ear and goes into the ear at the same place at different time, at the same time at different place, because wave can be spread out in space. So this is a totally different idea than particles. If I use a bullet, I shoot you, and if you get on a bullet, then you will not be straight.
Sharp.
You cannot have a bullet that will hit two people at the same time. It never happens. But wave can. So wave spread out in the space. So you cannot reconcile the pictures of a wave and the particles. And we always think that wave behave like light behave like a wave. Specifically, light would actually undergo what we call a diffraction pattern or interference pattern. Just like when the light when it goes through two small holes, when you shine a light on it, then you see spectral that looks like this. And it's a light which is spread beyond its shadows. So this is a shadow. So let's say if this is a wall, then you shine a light, then this is the shadow. So these are the shadows. So if light will behave like particles, when you shine light, then you won't see anything beyond the shadow. But the fact is not true. The fact is that you always see a spread. Then you always see a spread of of light beyond the shadow. We call this a diffraction. So let's say if we have 2 points of wave that goes through 2 holes, then these 2 holes will actually undergo interference pattern. So interference pattern. So light will display this interference pattern like water. So you see water, they have this interference where you have this mutual enhancement and yeah. So this is what we call wave phenomena. And then another very important characteristic about wave is that the energy spread out. The energy spread out, and it's like the wave has energy. Somehow the wave has energy carried along it. Then when wave is moving and spreading, you can imagine that the energy gets spread out. But if you throw a ball, then the ball will move in the direction, and all the energy are concentrated and moving along with the ball. Right? So it's like a bullet that hits you, it will never hit other people. But wave is not. Wave can hit you and hit you anywhere. Like. So the characteristics here is the energy of wave sort of like spread out. And another very important thing is that when you spread out, the energy of the wave is said to be continuous. Whereas the energy in the particle is discrete. It's sort of like energy are all contained inside, and it will not spread out in space. But in wave, the energy is sort of like spread out and it's continuous. Everywhere you find at this point, energy are all can be found. So this is a very sharp distinction between a wave and a particles, especially if you like, it's like you have water. The water you fill it up, so pipe fill up a tank of water, then the water will get accumulated and then will fill up gradually. So the filling up process is a gradual process which is continuous. The other way of filling up things is like you, instead of water, you say you have a lot of bits, small bits. So bakuli yang kecil-kecil, then you put in one by one. You put in one by one. So every time you put in one small bakuli. So this is like you filling up the thing discretely, whereas this you fill up and then the tank we call it continuously.
Continuous.
So this is like what the energy carried by the wave, which is filling up things continuously, whereas this is like discrete energy. So you throw a ball in it, then you have this much. You throw another ball, you have this. So every time you throw one. So this is discrete, this is continuous. So I will make sure that you understand what you mean by discrete and continuous. So continuous, when you finish, then you one lump, you throw in, then you have to throw it another time. So all these are individual. Yeah. So this is discrete. This is continuous. So energy carried by the wave is continuous, whereas energy carried by particles is discrete. Yeah. So that means that if you have let's say you have a patong here, somewhere patong. Then you want to knock down the patong. So you throw a ball. If the ball is hard enough, then you hit this and you will jatuh. If you throw it not hard enough, then you will not jatuh. So you are like throwing energy to a patong discretely. So either the energy is enough to overthrow the patong, or it will not. Right. So another thing is that you try to spray it with water. So you try to spray water. So water carry energy as well. And so water, if the water is not strong enough, you will never be able to overthrow it. Okay. I will try to give you some analogy.
The water spray the surroundings.
Okay, so then you try to compare this scenario and this scenario. So the water, since it's coming in continuously, so you can fill up the tank gradually until it overflows. So in this case, what is the difference between this and this? In this case, since energy is coming in, so actually it flows. That means the water supply can be accumulated. So you switch on the tap, then you wait. Then maybe 1 second, maybe 5 seconds later, only then the water can fill up. Okay. So water will get filled up, and then you can accumulate the energy. So this is only possible if the energy flows in continuously. So how? Okay. So this has to do with your questions. You say this, you say, imagine that you have a plate, a metal plate, where it has an energy. Where this energy has the particles. The particles somehow has a string attached to it, and this particles is called electron. Is bound to the surface by a string, and the string has a strength. So you want to kick out the electron from the surface. So obviously you need to provide enough energy to break the spring. So this is like throwing a stone. You throw a stone in, either you can able to kick it out or you don't. If your energy is not enough, you will not be able to kick it out. So there is a minimum amount of energy that is required to kick out the electron. But so you try to kick out the electrons by providing energy to the surface. So then it depends on how you provide the energy to kick out the electron. There are two ways. One way is by throwing stone on it. The other way is by filling up the energy, like water flow into from a hose and fill up the gap gradually. So there are two ways how you provide energy to kick out the electron. One is to throw in the energy continuously and let it accumulate. So there may be, say for example, some minimum amount of energy required to throw it up. So either you fill up at some rate, some supply of energy, you wait for a while for let's say some time delta T. So that when you wait for long enough, then enough energy is accumulated so that the electron that has enough energy would be kicked out. Or the other way is you throw a stone which is strong enough that is able to break the electron from it. Now from physics point of view, both methods, either you throw a stone to kick it out or to fill up the electron energy are similar in effect. It should be like because why? Because if you shine this with wave, then wave deliver energy continuously, as I said. So if the wave has not enough energy, then you just have to wait. You just have to wait the more because they fill up the tank gradually. So when you wait long enough, then the energy will be enough to be filled up. Then you will kick out the electron. It's just a matter of time to wait for the energy delivered to the electron.
Because it's continuous, so it was like gradually from small become bigger.
Yeah. So when it become bigger, the energy. So what is important here is you need to wait for a little while. It will not. The electron will not be kicked up instantaneously because you have to wait for the water to fill up. Once the water fill up, then electron, enough energy is deposited, then electron will fill up. So the other way is that you don't do this. You throw a ball in it, and immediately if the energy is large enough to break the electron, then it will kick up.
Then it will be discrete.
Yeah, it will be discrete. Okay, so now the question is, you think the light is continuous? Light is continuous by wave. So wave should deliver energy continuously. So no matter how strong is your energy, so you say you have a light, light could be have a strong light or weak light. So if you say you buy a very powerful light source, then it's very bright light. Then if the battery run out, then it become very dim. So dim light has low energy. Strong light has very powerful energy. So if you use a strong light to shine on the surface, you expect the electron will kick out very fast. If you shine it with a light, then you blink light, then the electron should be also be kicked out.
But take the time.
Yeah, that's what you think. So as long as it's a light that delivers enough energy, then electron will be always kicked out, no matter what surface it is. So you shine a light on it, then you wait, then you expect electron to be kicked out. There should be no threshold. No matter how strong the light that you use, it could be strong one or weak one, electron will always be kicked out. So that's why we say that there's no minimum intensity in the light to release the electron. You can have a low intensity or high intensity, electron will always be kicked out. It's just like you go to McDonald's, you want to buy a Big Mac. Whether you are 3-year-old kids or you are 80-year-old person, you always can buy a McDonald's. So there's no limit. Right? So it's just that old people walk slower, and young people walk faster. So you
take time.
Yeah, it takes time. So it's a matter of time if light were to deliver energy. But if you throw an electron, if you throw it with a stone onto the surface, if the energy of the surface is strong enough, stronger than the spring's energy, then electron will be kicked out. And if the stone is not strong enough, then electron will not be kicked out because stone energy cannot be accumulated. When you finish throwing, either you have enough energy to kick out or you don't. So you throw a stone, you wait. Either you kick out or you don't. You don't need to wait. So immediately, if you have energy enough in your stone, you throw it strong enough, then the electron will be released instantaneously. Right? Okay, so these are the general argument. This is what we expect to the surface electron if you were to kick out the electron from the surface. So what people did is that say, okay, now light is an electron. Light is a wave. So when I shine a light on the wave, I shine a light on the surface, I will always have electron kick out no matter what, no matter how long I wait. Okay. But then they don't see this. They see something which is very weird. They see three very important behaviors of light. That is, when they shine a light, they can use red light. Red light has a wavelength which is long. Red light has a long wavelength. So you have to understand this light comes in different color. The long red color until the purple color. So the purple color is the light which has a shorter wavelength. So red color light has a longer wavelength. So if you have a same color of light, that means you have the same color of wavelength. So now imagine this experiment. You take a light, say a red color light, you shine it onto the surface. Then you can shine it with a very high intensity or low intensity. Then you expect that if you shine it with very, very strong intensity with the same red light, you expect electron to kick out fast. Red light that is dim, but the same wavelength, you just put it a little bit longer. If you use a purple color light, you expect the same thing. You shine it with a purple color light. Intensity strong one, the electron will kick out immediately or very fast. Right? But what they find is the opposite. They don't find this. They find that the electron will be kicked out from surface no matter how strong is or how weak is the purple light. So as long as the purple light, as long as the purple light, the wavelength is the same. No matter how weak it is, how strong it is, the intensity, electron will always be kicked out.
So it depends on the time?
It doesn't depend on time. That is the second characteristics. There are three characteristics about this experiment. So you use same kind of, I need to write. So these are these experiments that they find. So they shine with a wavelength. Then what they do is they find that the electron will be either kicked out. There will be electron kicked out as long as the wavelength is less than certain number, no matter how strong is the intensity. So in physics, in more practical, what it means is you shine it with a very, very intense light. So let's say you have a wavelength, say a purple color light. So the purple color light has a wavelength which is very short. I think purple color light is I think 400 nanometer. Then you have a red color light. This is purple. Red color one, I think is 700 nanometer wavelength. So then this lambda would be some number. It would be like, I think say 500 nanometer. So they found that if you use a wave which has a wavelength less than 500, such as the purple color wave, then when you shine on the surface, no matter how strong or how weak your intensity of light is, electron always get kicked out. But then if your wavelength that you use a light color light, you have a wavelength of 700, which is larger than the threshold, then when you shine this wavelength with a very, very strong intensity, much stronger than this one, electron will not kick out. No matter how long you wait, no matter how strong the intensity you use, electron will never kick out. Right? This is what they found.
But actually, if like from what you have explained, it should kick out.
Yes, it should kick out. You should expect when you say you should kick out, because if light behave like a wave, the energy will get accumulated, just like water fill up the tank. And then there is a lag of time. But what they found is that only when wavelength less than certain threshold, it will get kicked out. And the second phenomenon is, you see the first phenomenon is the existence of a cut-off wavelength. Below the cut-off wavelength, light will be kicked out, electron will kick out. If you use a light which has a wavelength larger than the cut-off, then the electron will not be kicked out. The second phenomenon is that when they do the experiment, they measure the electron instantaneously without waiting. So for example, you use a very, very weak intensity light, very, very weak intensity purple color light. No matter how weak it is, as long as it shines, immediately electron get kicked out. So these are the two.
Dia ada certain benda ke yang macam baca word function, they use whether the zinc or sulfur or calcium to sodium to break out the electron band.
So you tanya surface ni lah. So what are the surface? So you tukar surface dengan you ada aluminium surface, you ada lithium surface. So this is come as a third characteristic. So for this experiment, there are three characteristics. First is the existence of the cut-off wavelength. Second is that the electron get kicked out immediately. Thirdly is that if you use a different material, plate, the cut-off wavelength will change. So this is a phenomena that people observe. So from this phenomena, this experiment, you have a lot of controversy because light behaves like this, it should not behave like this. But if you compare it with throwing the electron with a stone, then the experiment result seems to agree better. So you have a wavelength which is less than cut off. Then that means it is like you have a stone that has energy strong enough to kick out the electron. If you use a wavelength which is larger than the cutoff, it's like you throw the electron with energy not enough to break the spring. And then if it's a stone, when you kick out the electron, it will be kicked out immediately. The stone will not need you to wait because it doesn't need like water to fill up, take time to fill up. Electron will just deliver electron energy immediately. So this experiment, it makes you feel like as though the light does not behave like what is predicted if it were a wave. It's more like a particle behavior. it delivers electron energy instantaneously, and then it will either kick out or you don't.
Okay.
And then no matter how long you wait, the energy will just not get accumulated. So then this is the first piece of evidence, 1904. I think 1904, during that time, people carried out these experiments, and then they cannot find any explanations.
Conclusion.
They cannot find because the experiments show a very sharp controversy as though it's a sharp controversy because you don't expect the light to behave like that, because you expect light is like a wave, but light being a wave, it cannot be explained. It cannot even be used to explain this experiment. So people got into controversy. So then someone come up with explanations, 1905, and then he solved this problem by giving some propositions, and then he got a Nobel Prize for that, 1905. It's called the photoelectric effect.
Oh.
Yeah. So first I have to understand what you mean by photoelectric effect. So photoelectric effect is this effect that I mentioned just now. So now you should be able to understand what you meant by photoelectric. It's experimental finding. So exists a threshold, and then no matter how long, no matter how strong is the intensity, the threshold. So normally these three experiments, these three phenomena, 1, 2, 3 characteristics, is summarized into graph, into 3 graphs. I think the first graph is the existence of a threshold. Then then you need to understand the experiment, how they carry out the experiments. So what they do is they have a metal plate. I think they have a plate, right? So then they shine a light on it with a wavelength. Then on this part, they expose this to a positive state. Means exposed to negative, positive. Okay, so this is the tube. So what they do is they shine a wavelength. Then I think then the electron will kick out.
That is
this is negative, I think.
Dr. Yoon.
Yeah. So somehow there is this current flow in the direction of particles. I think I'm going to draw this out. So the idea is electron will get kicked out from the surface if wavelength is short enough. Then electron get kicked out. It will travel because of the heat. It will travel again in this direction. So you can measure the electron. The electron will be measured from this side to this side. So what you do is you try to, because the electron will move, right? So electron will move with some kinetic energy. Then say if this is negative, so if this is connected to negative, then electron, okay, let's say if this is a low battery, so electron that is being kicked out will travel towards here. Then you will measure the current. So what they do is they measure the current. For different wavelengths. So they find that when the wavelength is less than some cutoff, you got some current. But when wavelength is larger than some cutoff, there's no current. It just means that when wavelength is smaller, then the current will flow. And if wavelength is larger, then the current will not flow. That's what it basically says.
So if the wavelength should be smaller than the current.
No. I think as long as electron are kicked out, then current will flow.
Electron has kick out juga kan? Dia akan terbebas juga.
Asalkan dia bertenaga cukup, dia akan tenaga luar. Asalkan dia bertenaga cukup, dia akan tenaga luar electron. So if you have a current flowing. Okay, so then what you want to do is to be more specific. You want to measure if the electron is kicked out, what is the kinetic energy of the electron? So it's like this. So if you have electron attached to it, then it's attached to it with a spring embedded in it. So to break the spring, you have to pay the penalty, because it's like you want to you want to say if you want to jump out from the gravity on the surface, you jump, and to jump hard enough, or else you will not be able to live. Right? So it's like electron, in order to leave the surface, we have to have enough energy for it to kick out. Okay, so imagine that you the light deliver the energy of this much. Then some penalty has to be paid for this electron to get rid from the surface. So that means your energy has to be larger than the penalty before you can kick out the electron. So if the energy is larger than the penalty, then the electron will be kicked out. So the energy that you pump in to kick out the electron is related by this. You put in that amount of energy by wave, by the light, then the electron that's kicked out will move. Electron that move has energy. We call this a kinetic energy. Yeah, last 2 weeks we mentioned any particle that's moving will have energy. We call it kinetic energy. So this kinetic energy is the difference between this one and this one. Yeah, I think it's just like you. It's just like you have say for the kids, then the father gives $10. Then he gets the money. He wants to go to the school, so he have to pay the ticket for the bus. The bus is $1, so you have to pay $1. Then when you go to school, you have to pay $9. So you expect that the kinetic energy from the that we measure from the surface would be a difference between the energy provided and the penalty that is used to buy the electron. So you have this very simple relationship. You measure the kinetic energy here. You can measure the kinetic energy. The kinetic energy is measured like this. If you impose a potential between them, this potential is like battery. You can tune the battery to make it larger or smaller. The battery can 1.5 volt, 7.5 volt. So what you do is you try to tune the voltage such that when the voltage is the same, if the voltage times the charge is the same as the kinetic energy of the electron, then the electron will not be able to reach here. So electron get kicked out, it will move from kinetic energy, but this voltage will try to oppose its motion. So if the voltage is strong enough, then electron will never make its way to the other side to complete the current. So this is how people do the measurement. They want to measure the kinetic energy of the electron to kick out from the surface. So what they do is they impose a voltage between these two, and then they tune the voltage such a way that they want to know what is the voltage where the electron will never reach there. If the voltage is small, then the electron will reach there. If the voltage is just nice enough, then no electron will be able to reach there. So then the electron will just hop and then no more current. So people, by tuning this voltage until no current flows, then they will be able to know what is the kinetic energy of the electron. So basically, you perform this experiment, then you impose a voltage, then you tune it until you don't find any current. That allows you to measure the kinetic energy of the electron. So they find that the kinetic energy of the electron can be measured using this method. Then they find that the kinetic energy, according to this argument, that the energy delivered to kick out the electron have to obey this relationship. So the kinetic energy of the electron will be the difference between the energy that comes from the light minus away the penalty for the electron to leave the surface. So this have these two relationship. So this is what you measure from the experiment. This is what assume this from conservation of energy. So what they found is that the kinetic energy that they measure do not depend on the intensity of light. Right? The light, no matter how intense it is, it can be very, very long, very, very intense, but the kinetic energy that we measured always the same. So you have this graph. The graph looks like I think this is the graph. The graph on this figure 2.10. That is, no matter, the graph looks like this. That is, no matter what the intensity is, this is I think I naught, 2 I naught, 3 I naught. If the intensity is very large, then the potential, the stopping potential that you measure is always the same. So this graph, it carries the information that no matter how strong you shine a light on it, the kinetic energy of the electron will still remain the same. But this is a controversy because you expect the stronger the intensity of light.
Higher the effects apa? Dia punya word tu.
Yeah, you expect that. You expect jika you pakai intensity yang lebih besar, lebih kuat punya cahaya, kuat in the sense that dia lebih cerah, lebih terang, keamatannya lebih tinggi. Jika you pakai light dengan keamatan yang sangat tinggi, you expect elektron punya kinetic energy akan bertambah. Yes. But you don't find it. You find the opposite. You find it's always the same.
Always same.
Yeah. So this is puzzling, and then if the wavelength, if your wavelength, this is for wavelength less than cutoff. But if your wavelength is more than cutoff, if the wavelength is more than cutoff, what do you get? You get nothing. If the wavelength is more than cutoff, you get nothing. You don't measure any electron. You don't have kinetic energy at all. You don't have current flow at all. So, and then as long as your wavelength is less than cutoff, no matter how small your intensity is, you always have the electron pick up, and the kinetic energy of the electron is always the same. Okay, so this is one of the examples that shows that your electrons are being hit up by light, as though the light is not a wave. Light behaves more like a particle in this sense. So this is photoelectricity. Okay, so I think the idea is like this. So then if we go to the next bit, is about not too much about the physics, it's about formula. You need two formulas for this photoelectricity. One formula is like this. That is the formula for the electron voltage is the total energy of wave dosing minus the work function. W is the work function. You have, let's say you have a surface one, electron that has to pick up have to pay the penalty of work W1. If you have a different surface, then you have to pay another voltage. It's just like this is the this is the toll number 1. Then for toll number 1, you pay $1. For second type of toll, say in KL, you have to pay $2 toll. So different surfaces are different toll, you have to pay different penalty. So you expect that if you shine the same light, for example, shine the same wavelength of light onto different surface, the kinetic energy will be different because the kinetic energy is the difference between the wave and the wave function. Right? So if you shine the same light with the same energy onto different surface have different tone, therefore the kinetic energy of the electron will be different. So we have this one formula, then we have another formula which is most important. That is the energy of the light. The energy of the light is given by this H over lambda. So which shows if you shine a light with a wavelength lambda, then the light carries energy, and the energy of light is given by H over lambda. Now this formula is a very weird formula, which is not in existence at all before 1900. So this formula, it relates the energy of a light to its wavelength, and this is
H is height, is it?
H is a constant. It's just a constant.
Yeah,
Planck constant.
Planck constant.
No, we call it Planck constant. Planck constant.
Planck.
So this formula, it actually refers that the energy of the electron behaves like it's a discrete particles. The light behaves like the particles. The energy carried by the light is as though it is the light is a stone which has a discrete energy.
But light should have continuous energy.
Yes, this is what you think. Light should have continuous energy. It should not behave like a stone that carries discrete energy. But in this case, in order to explain the photoelectricity effect, you have to assume, you have to explain the photoelectricity effect by assuming the light to have discrete energy like a stone. And the discrete energy of a light is related to its wavelength. So this relationship between the energy of the light and the wavelength is a very weird one. And it only exists in 1900. It actually is proposed in another experiment called Planck experiment. But you just accept that the light carries energy given by h over lambda. H is a constant. And this is a formula that relates the energy of the light to the wavelength of the light. So then you have this formula. Then it explains the fact that different particles, different surface have different wavelength. So I think what else formula is different formula, and sometimes because the light right, is moving with the speed of light c, and then it has a wavelength of lambda. And light will also have a frequency. So the relationship between the light speed and the wavelength and the frequency is given by another formula, c equals to f lambda. So this is the relationship that you should memorize. It relates the speed of light to the frequency and the wavelength. And the speed of light is a constant. So you can also write this formula as c over f. Sometimes the f is written as mu. H mu over c. So I think some h over lambda, and then lambda is c over mu. So energy is related to the frequency or is related to the wavelength for light. So we have these two equations. Then there's third equations that we have to write down. It is the work function. The work functions, I think that's all we need. So we combine these two equations. Then we have this equation called h mu over c is equals to E lambda. And then E lambda is EV plus WV. And EV is just your kinetic energy. Okay, EV is the kinetic energy of the electron plus the work function and h mu over c. So you have this formula that looks like this. So you have this formula. So this formula is, so what I have done is I just have combined this formula with this formula. These two are two different formula. And then I also make use of the fact that frequency and wavelength and speed of light is related by this. So then I'll just divide it, then I got these equations. Now this equation is what we have found in 2.8. So when you look at the equations in physics, you don't just remember or memorize it. You try to understand what each term means. So this term means this you have an experiment, you have a surface, you have a light that comes in. Then when light hits on the surface, electron will get kicked out, and then you can measure the electron kinetic energy. And the surface has a work function that would bind the electron to it. Okay, so what this means is that you plot Ke equals to h mu over c minus w. Okay, so what you do is you carry out experiments. So lambda is a wavelength. So lambda is related to the wavelength through c over mu. Okay, so you use a frequency, a fixed wavelength is the same. So you shine the surface with a fixed frequency of light. Then you measure the kinetic energy. So this is what you do in the experiment. You shine a light with a given frequency, say 1000. Then you measure the kinetic energy using the method I mentioned, the potential method. So imagine that this is what you measure. You have kinetic energy, then you have a frequency. So you fix the frequency, then you measure kinetic energy, then you get 1 data point. Then you carry out the experiment again by changing another light. So you shine it, you say the purple color light, then you use a different color, blue color light. Then you have a different one. Then you carry out another experiment, have a new point. So then you find that you carry out this experiment, the experiment gives you a straight line. And then this straight line can be just explained by this formula. That is, when you fix the frequency like this, kinetic energy versus omega. So you find that the graph looks like this. So in this experiment,
lab.
Single
sleep and double sleep.
No, this is not you measure the frequency and kinetic energy.
Go see.
Then you find that the graph would be like this. But this graph is described by this formula. And this is the y, this is the x. And this new is sorry, and this is not this is called frequency. It's called frequency. So the slope of the frequency is h over c, the slope.
Okay.
And then at this particular point, the kinetic energy becomes 0. It is when h equals to some fixed frequency, then the kinetic energy becomes 0. And you cannot measure anymore. There's no, because electron has no kinetic energy. So you carry out this electron experiment like this, and you draw a line. And this straight line of experiment is well described by this formula. So you can then explain why there exists a threshold frequency. That is, when the frequency is less, if the frequency is more than this one, then only electron will kick out. If the frequency is less than this threshold, then no electron will kick out because electron kinetic energy cannot be negative. So that explains the existence of a cutoff, because the existence of a cutoff, like I just write like this. So this is the same as C over new cutoff. So the cutoff in the wavelength is the same as the cutoff in the frequency. So the cutoff of frequency is opposite. Say your wavelength have to be larger, has to be smaller than the cutoff. Only then you see it. Equally, you say the frequency has to be larger than the cutoff. Only then you have electron kick out. So this graph, this formula explains very well the photoelectric effect. And when you when you do this experiment, when you do this equation, it doesn't involve intensity. So let's explain the experiment. So I was telling you about all this controversy of the light and whatever, and this controversy in photoelectricity experiment. So the solution in that is in these equations. So this equation explains the photoelectricity effect completely. The thing that you need to realize is when you write down this equation to explain the photoelectricity effect, you assume the energy of the photon is given by this formula. And when you do this, you are already giving up assuming light as a wave. Yeah. So this assumed light now behave like particles. If you give up the light as a wave interpretation, then everything is explained totally well, and you do not need to wait for electron to be kicked out. It will kick out immediately because now particle give a light. And then you can also explain the existence of a cutoff frequency. So this formula explains the cutoff frequency, the existence of cutoff frequency. As long as the frequency is larger than the cutoff You always see a photoelectricity. If it's less, then you don't see. So you explain this photoelectricity experiment at the expense of giving up light as a wave. So that is what the photoelectricity is. This is a cut-off one. But this
but here, they give KE max. Do we have to write? Do we need to write in the exam like max or no?
Rasanya kelas kita ni.
If you want to explain why is K max actually is slightly more than because electron has traveled.
So the point here is the maximum photoelectron energy.
Yeah, because the electromagnetic energy that
KE max.
The potential, the kinetic energy is more than W because electron may come from below. It's not on the surface. When it comes from below, it takes extra energy to travel. So that means it needs more energy to. To refer to it like the kinetic take by electron on the surface to leave. But if you have electron at the bottom,
it needs more than the one in the surface.
Yeah. So the electron kinetic energy that leaves the surface would be in general less than what is predicted. So the maximum one would be the electron from the surface. The electron from the surface would have the most largest maximum, have the largest kinetic energy. Electron that's coming from the bottom of the surface would have to pay larger energy. So let's finish the part of photoelectricity effect. So let's see, it talks about light behave like wave. So these are all properties of wave. Yeah.
Oh, nampak.
So when you read the books, the book comes in sections. So each section has a meaning. So as long as you know enough, that means you know enough. Yeah, the concept. So this is the concept. So for example, it shows you this picture of this type of picture. The purpose of the discussion in this picture is just to make you aware of the nature. Yeah. So wave behaves like this interference. Particle don't, and wave takes time to deliver energy.
Monochromatic light source means monochromatic means one, is it?
One wavelength.
Mono?
One wavelength.
Mono.
No, it means the wavelength is
monochromatic.
it means the wavelength.
One source.
One source. No, it should be more specific than that. It should be that the light that comes from the source has only single wavelength. Yeah.
Single wavelength.
Like light from this source is not monochromatic. It comes in different wavelength.
So let's say if you like how we did the experiment in the lab with single slit and double slit, so there is light coming, right?
Yeah.
So that is called mono.
No, the monochromatic has nothing to do with the numbers of slide. It has to do with the light source. This light source is not monochromatic because menthol is not monochromatic. Because the light source will emit up with various wavelengths.
What is monochromatic?
That means the light source give out only light that has only a sharp wavelength. Say the light.
Laser.
Yeah, laser. The other good experiment would be the natrium light. The natrium light wavelength is very sharp. It's like only one or two wavelength. I think 400 something, 355 nanometer, and we don't have other wavelength. So most of the light that we see in our daily life are not monochromatic, including your light source, white source, your torchlight. But laser light, these are monochromatic wavelength. Very little time we see monochromatic light. But in experiment, you can have this monochromatic light. One way is to use natrium light. Natrium bulb. These are light source that has,
which is monochromatic.
Yeah, more approximately, because the wavelength is sharp. It's not like very diffuse. The light from the sun appears like white because it's a mixture of all wavelength. So when you mix up, then it becomes like a white color. So the neutron light looks like yellowish because the light source has a wavelength that falls into the color of orange. It has no wavelength on other wavelength. So light source of LED also is monochromatic, more or less. So you have a LED light.
Oh, LED bulb.
Not white color one, the blue color one, red color one. You have red color LED. So it appears red because the light that comes out from it have only red
Same
wavelength.
color.
When they say same color, it means the same wavelength.
Okay.
So this is finished with the photoelectricity effect. But this is only one experimental evidence that hinted on the fact that light do not behave like wave as we expect.
Yeah.
There are other experiments that also hint on this. The other experiment will be on Planck's black body radiation. Yeah, black body radiation. So black body radiation is another experiment that infer light does not behave like wave. Specifically because in order to explain the black body radiation, you have to assume that the light carries energy in its discrete form. It's just this formula. This formula. When you write down this formula, it assumes that light behaves like particles. So if you assume the light carries energy, then described by this formula, then you are giving up light behaves like a wave. So in order to explain the black body radiations, the explanation requires light to behave like the particles. It's very similar in argument when you talk about the black body radiation. You compare the argument with the photoelectricity effect. The photoelectricity effect is the same. Photoelectricity, you have an experiment, then you try to explain it by using conventional wisdom. Light behaves like a wave. Then you fail. Then in order to explain it satisfactorily, you have to treat light as particles. Similarly, in black body radiation, you think light is a wave. Then you start to explain the black body radiation experiment using light as a wave. But then you find that no, it doesn't explain, it cannot explain. Then you are forced to adopt a new paradigm that particles, that light behaves like particles and carry this energy. Then we find that you can explain the black body radiation experiment very well. So I have not told you what is the detail of the black body radiation, but basically it's experiments that can measure something, then you try to explain the results using conventional knowledge and you fail. So in that particular case of black body radiations, the experimental result is what we call, the experimental result is not a photoelectricity effect, but in black body radiation effect, the experiment that we try to explain is called R lambda versus this is frequency. The first frequency. We measure this thing, then we find out the behavior, the shape looks like this. So when we find that the experiment result looks like this. So they try to explain this experiment by assuming it light to behave like a wave. When they do that, they find that the predictions will behave like this. So this is a prediction of theory by assuming light to behave like wave. So if you assume light behave like wave, theoretically the radiance versus frequency will move like this. But experimentally you see this shape. So which is totally different from what you expect from theory. So now I have to tell you what does this mean. It means is you take a piece of body, let's say a ball, then you heat it up to some temperature. So say 1000 degrees. Say bearing, say a bearing made of steel. You heat up to 1000 degrees, then of course it becomes very hot. Then it radiate all this heat. You can feel the heat from this. So what they do is each of this heat is a radiations light. So what they do is they measure, they use some experimental setup that allows light to go through a small hole. Then the light will go through this small hole, and then it detect the wavelength. And then how much is the wavelength? So basically, they detect the intensity of light at a fixed wavelength. So you could have say wavelength in say 500. You could also have wavelength at say 560, wavelength at 570. So this hot berry emits light, very hot light at all wavelength. Various wavelengths, like the sun, it emits light of various wavelengths. But there are some wavelength has high intensity, some wavelength has low intensity. Like I think in our light, I think in the morning, the intensity in the infrared, also in the ultraviolet is less. In the afternoon, in the evening, the intensity of ultraviolet is higher. So different wavelengths have different intensity in the light. So they carry this experiment. Then they found it looks like this. It looks like this. So this is what they call. So instead of I think they somehow become radiance. So they measure this one, but theoretically you have to explain this one because R lambda is for the experiment measure, and then they just do some manipulation. Then you got so they got this from this. So anyway, you can imagine this to be the same intensity. Intensity of the black body radiations at different wavelength or at different frequency. It's the same at different frequency or different wavelength. It's the same. So it's like wave. Right. So for example, wave of say 500 nanometer. It has a frequency of say 10 power of 13 hertz. Wavelength of say 600 nanometer, it has a frequency of I think of say 12 hertz. So you specify the wave of the light either in terms of wavelength or frequency. It's the same thing. It's just like you spray this in terms of radio, this in terms of sound. It's a different unit. So they measure this one, then they try to explain graphically. You assume light is wave, but then they cannot explain. They always have this line that looks like this. So then they fail. Then someone come up in 1905 called Planck. He can explain the spectrum. This is called the spectrum. He can explain the black body radiation spectrum by assuming that the energy of the light is given by this formula hc over lambda or equals to h frequency. It's the same formula that I wrote down just now. Then by using this assumption, then he got a very nice curve theoretically that can explain the experimental finding. So the story goes the same. You give away light, behave like wave, and assume light to have energy like this, then you explain the equation very nicely. So then you have the second hint for experiment that light doesn't behave like wave. Its energy, because its energy is discrete, and this is in opposition to light being a wave. So in both cases, in both experiments, light behaves like corpuscular particles that carries energy which is discrete and given by this formula. E equals to hc over lambda. So that finished the part on black body radiation. There's a lot of technical details on this formula, but I don't go into this. It's very complicated. It involves statistical mechanics. But the idea is like this. Then we have this second experiment that light behave like particles. Then we have a third experiment that also show light like the particles, which is called X-ray. So X-ray is also an experiment that shows the light behave like particles. Yeah. So the X-ray is another experimental evidence that shows that like the light is like particles. So the X-ray was discovered in around 1900, and the first Nobel Prize is given to this X-ray. X-ray you can choose. And then the fourth experiment that shows light behaves like particles is Compton effect. So we have this Compton effect, 2.7, page 75. So this is also like a particles, also is the experimental evidence to show light behaves like